Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Someone trickling in here. Let me let them in. Yeah, okay. So let's actually jump right into it. Just a heads up, tomorrow is when I'll be dropping your projects, putting you guys in groups. So that should be interesting. And at the moment, I don't really have anything else to say about that. So let's actually just jump into it. Okay, there we go. Just make sure I can see the chat. So today is going to be somewhat of another information dump class where I'm going to tell you all these concepts. I'm going to talk about them. It'll be a little bit more dynamic than the last one that we had. So the last one that we had, I just told you, definitions of a set. Here's what a subset is. Here's this. But now it's going to be a little bit dynamic because I'll give you examples as I'm going along. It's going to seem very mathy at first and kind of like, what is this about? But then hopefully with my examples, it'll clear up when and how you would use the things that I'm talking about. So we are still on basic counting principles, and we're going to cover most of the counting principles that we want to know about at the end of today. A little bit of that might spill into tomorrow, and tomorrow, in addition to putting you in your groups, I will go through some counting examples for you. Maybe even put you guys in your groups for you to figure out a couple. And yeah, so for now, we're going to continue with 7.3, 7.4. We spoke about one thing so far called the multiplication rule. It's actually a super important rule. In fact, the next two rules I'm going to derive can be followed from the multiplication rule. So the multiplication rule says the following in terms of like the math language behind it. Suppose you have two sets A and B, and you want to create a tuple where, say, the first coordinate always comes from A and the second coordinate always comes from B. How many possible coordinates could you create, right? How many possible pairs? And that the answer was the size of A times the size of B. Take the number of things in A times the number of things in B, and that's how many ways you can actually do that. We could generalize this to n sets. So if I have n different sets, potentially, A1 times A2 times A3 all the way up to AN, how many ways can I create n tuples? A1, A2, A3 all the way up to AN in a coordinate. How many ways can that be done? Well, it's the number of things in A1 times the number of things in A2 times the number of things in A3 all the way up to the number of things in AN, okay? And that is can be expressed in this way here. If an experiment has m stages, and you know the number of ways that the first stage can happen, the number of ways the second stage can happen, the number of ways the third stage can happen, and so on, all the way up to the mth stage, m as in mom, then the number of possible ways that the overall experiment can go is n1 times n2 times n3 all the way up to n sub m. Right, so that's called the multiplication rule. And this definition here, this last definition is the kind of the more intuitive way to think about it, right? So, you're looking at something and it has several parts to it. And this is the number of ways that this part can go. And this is the number of ways that this part can go. This is the number of ways that this part can go. How many ways can the overall thing go? Well, you just multiply the number of ways across them. That's more intuitive. But understanding that it's creating a tuple, it's equivalent to actually creating a tuple is going to be important for applications. So like I said, we defined sets as collections of things that had no inherent order and no repetition, whereas a tuple has order and repetition. So there are certain applications where you want to think in terms of tuples and certain situations you want to think in terms of sets. So the idea is if you're thinking of counting a possible tuple, then you would think things like the multiplication rule. And so that's that. And we did an example here. By the way, we did some examples where we constructed things like tuples before, like the boy-girl problem, right? So the multiplication rule would be how we counted things in the boy-girl problem, right? Because I didn't want to think of it as sets of children because I wanted to be able to repeat the sets and I didn't want the repeat to be lost. I also probably cared about order. I cared about the older child versus the younger child. So visualizing that situation, tuples was what I wanted to use. And so something like the multiplication rule come in handy there. So I stated it both ways because thinking in terms of tuples and sets is going to be useful. But let's actually move on. So we're going to continue basic counting principles. We are going to talk about, just get my notes ready here. We're going to talk about some more basic counting principles as well as permutations and combinations. I don't know if you guys have seen these things before, but you're going to see them now. So you're going to learn today. Let's continue with the multiplication rule. Implies the following two rules. Here's a rule. Suppose a set has a set A has n elements. Okay. Then the number of, I was going to say M, but let's do R because I can't be bothered with, oh, M as in mom or N as in Nancy. Like if I say N and M, I don't want you guys to get mixed up. So I'm going to use another traditional letter used is R. Some sources would use K. M is pretty common, but it's nice when you're reading it. It's not nice when someone is saying it and speaking it to you. So the number of R tuples that, the number of R tuples where I want it to be known that R is less than N, less than or equal to potentially. So A1, A2, up to AR. So I'm taking elements from this set, perhaps not all the elements, but some, and I am arranging them into a coordinate of size R. The number of R tuples that can be formed from the elements of A with no restriction. I'm going to put a restriction on it later. With no restriction is n times n minus 1 times n minus 2 times ... times n, no restriction. I was doing the restriction one. It's actually a lot easier, n to the r. And y, we're creating, it's like an experiment and we have stages, we're creating a tuple like this, where there are R slots. Then, how many things can I put in the first slot? Well, there are n things in the set. I can pick any n of them and put in the first slot, n choices. Now, there's no restriction on what I can choose for the second element, so I can pick any of the n things and put it in the second slot as well. pick any of the n things and put it in the second slot as well. I could even pick the same thing every single time and put it in, right? So I have n choices, n choices, n choices in every coordinate. The multiplication rule says this is n times n times n times n r times by multiplication rule. So that is just n raised to the r power, okay? Because I'm just multiplying how each stage can go n ways. And so if I multiply r stages, multiply the number of ways that r stages could go, I get n to the r, right? So that's why. Okay. Let me give you a simple example here. Suppose phone numbers are 10-digit numbers with no restriction. So you can create whatever phone number you want by arranging 10 numbers in order, right? So literally 00000 10 times is a phone number according to this definition. It's not, but just for the sake of this example. With no restriction on the digits. How many possible phone numbers are there? Under this assumption. Now, if I had asked this counting question, there are some things I would want to go through your mind to know that we are going to be thinking of something like a multiplication rule or something like a tuple. So one, I want you to note, order matters for phone numbers, right? So someone can have the same digits in their phone number, but if they're rearranged in a different order, it's a different phone number, right? You're not going to, if you have, 10, 10, 3, 4, 7, 9, 2, 2, 5, 4, and then you call that number in any order of those guys, you get all the people with those digits. That's not how it works, right? The order matters for the phone numbers. So this kind of hints we should use sets. We should use tuples, not sets. So I would never think of phone numbers as a set of numbers, right? Like I would never think of someone's phone number as a set of numbers, because the set it doesn't care about the order, as well as it's going to get rid of repeats. So if someone has 2 2s in their phone number, the set will just count one of the 2s. That's the other thing that you would note. Also note, repetitions must be allowed. And again, that means we should use tuples, not sets, right? So when it comes to counting stuff, this is one of the levels in which I want you to be thinking on. Is it good to visualize this as a tuple or a set? And the thing is, if order matters or if repetition should be allowed, a tuple is better, right? That's basically the idea. So here I know I should be counting tuples, and I know that the multiplication rule deals with tuples, and I know this thing comes from the multiplication rule, so that's why I'm thinking these kinds of things. So this means a phone number is a tuple with 10 slots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And because there are no restrictions, I can put anything in any of these slots that I want. So in the first slot, I have 10 choices, right? All digits from 0 through 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So again, because there's no restriction, I can choose any of the 10 digits here, any of the 10 digits here. And going down the line, I can put any 10 digits in every position, right? No restriction was the situation we were in. Okay, so this means the number of phone numbers is 10 raised to the 10, which is a huge number, actually. It's a lot. Like, you wouldn't want to actually write down all those number of numbers. I don't really know of anything close to 10 to the 10. But I guess to give you some perspective, which is still kind of far off, but it starts to tell you, if you were to count all the grains of sand on the planet, you'll have about 10 to the 18, right? So 10 to the 10, right? You're a little over halfway. Well, not really, because you're not multiplying by twos. But in terms of how your powers are counting up, you're a little more than halfway to there. 10 to the 18 is actually way bigger than 10 to the 10. 10 to the 18 is like 10 billion times larger than 10 to the 10. But 10 to the 10 is actually pretty huge as well. But that's the number of possible phone numbers that you can have, right? So, yeah. If you were to randomly guess a particular person's phone number, yeah, you wouldn't, the chances of you getting it is not very high. So yeah, that's one counting principle. How to create tuples of size r from a set of size n with no restriction. There are n raised to the r number of ways you can do this. Now let's talk about an important restriction. No repeats. There are going to be times where we don't want to actually allow repeats. We might want to have order, but we don't want repetition. And I'll give you some examples of this later. So this leads to the second rule I was going to mention, rule 2. So far, these rules don't really have a name, but rule 2 is going to be an important number. So suppose A has n elements. I don't know why I exclaimed there. Getting too excited, Jhevon. And that, again, r is some integer less than n, right? Then the number of r tuples that can be created from the, maybe I'll put this down here. So I want the number of r tuples, A1, A2, all the way up to AR, that can be created from the elements of A with no repetition. That's very important in this scenario. So before I gave you the unrestricted number, right? Where there was no restriction, you can pick anything you want. However, now I do give you an important restriction. You're not allowed to repeat. Once you pick a number, you're not allowed to pick it again. Then the number of R tuples that can be created from the elements of A with no repetition is n times n minus 1 times n minus 2 times ... A lot of students think that this should end with n minus m, but it shouldn't. It should end with n minus m plus 1. And I'm going to explain why. Again, we're creating an R tuple. So there are R slots. Now, I'm picking things from a set A, which has n elements. Now, at first, I can do whatever I want. I can pick whoever I want. So to put something in the first position, I have n choices. However, I'm not allowed to repeat anything. So once I pick the first thing, the set that I can choose from now decreases. I'm not allowed to pick that thing again. So now I only have n minus 1 choices. In a similar vein, if I were to put the third guy in, I'm not allowed to pick any of the previous 2 guys. So this is n minus 2 choices. And this keeps going, right? Now, if I were to see how to count this, if I have R slots, well, notice that in the first thing, I had n minus 0 things I could put in there because there was no restriction on the first one. Then I had n minus 1, n minus 2, all the way up to. But if I start counting at 0, to make sure I get R things, I have to stop counting 1 less than R, because then you would have R things. If I go from 0 up to R minus 1, there will be R things in that list. So it goes up to n minus R minus 1, right? So I'm counting from 0 up to R minus 1. That gives me R things, R slots. And then if I were to expand the parentheses, the negative sign will come out and multiply the minus 1 to give a plus 1. So you have n minus R plus 1, which is, I was using n in the other class. So that's where the plus 1 comes from, because technically we start counting from 0, because for the first guy we had no restriction, and then we count up R things. So you'd have that. So this leaves you with n times n minus 1 times n minus 2, n minus R plus 1 as the number of possible R tuples with no repetition. Okay. Now, this number is actually a super duper important number. And math people, whenever there's an important number, we like to give it a special name, special notation, that sort of thing. So the above is a very important number. We denote it by P of NR. And some other notations. You can have NPR, 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 P, and R, etc. But you're going to have very similar symbols. Also, instead of R, M or K is also commonly used. But that's what you would see. Now, what you guys can do is make sure that you can find this number on your calculator. So your calculator should have that symbol either on the keys. If you have a very sophisticated calculator like a TI-89 or something like that, it'll be in a hidden menu. So on the TI-89 or TI-84, I think it would be under the math menu. So if you have that, you can make sure you can find it because it's going to be very important for you to be able to find this number. You click on math, then you would scroll to probability, and then you would see this symbol in there. I believe you'd see NPR. I think on your TI-89, this is the notation that's used. But on other calculators, you might have similar notation to the others. Okay, so it's actually a very, very important number. And it is called, what is the P for? It is called a permutation. So now that's the math definition, but let's actually bring it down to more intuitive applications-based kind of thing. Why is it called a permutation? Why? Because the root word is permute, which means to rearrange, right? So permute means to rearrange, right? So if I say, okay, I had these things over here and I created another permutation, what I just said to you is that I just created a different order. I just rearranged the stuff, right? So I can say I permuted these things, means I rearranged them. I put them in a different order. And that is the important kind of thing that I want you to realize that this number is counting. So i.e., P of NR is counting the number of ways to choose R objects from N objects in a particular order. Okay. Without, of course, without repetition. Let's just emphasize that. Right? That's what that number is counting. So, example. P of 50, 10, right? If I wanted to compute such a number, where would such a number arise? Well, for example, if I had a pile over there of 50 books and I wanted to start getting organized, I want to put books on shelves, and this shelf can only hold 10 books, and I wanted to say, how many ways randomly could I pick 10 books from that pile of 50 books and put them on this shelf? Of course, the books would go on the shelf in a certain order, right? So what I'm asking is, out of that pile of 50, how many ways can I take 10 of those things and arrange them in order, right? This is P of 50, 10, is the number of ways to choose 10 books from a pile of 50 books and arrange them on a shelf. For example. Okay. So notice, if I were to ask you that question on an exam or a test or a quiz or something, which we don't have quizzes, but you get the idea. If I were to say, okay, I have a pile of 50 books. How many ways can I pick 10 at random and arrange on a shelf? You should be aware that, okay, order definitely matters because how you arrange them on the shelf is going to matter. And two, there's no repetition. Once he picks up a book from the pile, that book has left the pile. He would have now 49 books left to choose another book from. Then when he picks a book, he would now have 48 books to choose from. He won't be able to pick a book twice. So there are no repeats and the order matters, right? So this tells you that you should be thinking of permutations. And it can be, you don't want to have to count these one by one, how many ways you can do this, but you do want to know that that would be what you're counting. So if you want to count how many ways you can choose from a set of things and put them in a particular order, this is the number you should be thinking about. If you want to know how many ways you can choose from a set number of things in a particular order, but you're allowed to repeat things that you chose, then n to the r is what you would choose. If you're not allowed to repeat, PNR is what you're allowed to choose. And that's very important. That's kind of giving you the intuition. There's a special case of this. And this is the case that your R is actually equal to the N. That is PNN. So that's going to be N times N minus 1 times N minus 2, dot, 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 going all the way down to N minus N plus 1, right? So instead of R, I pick N as the R. In other words, from that pile, I'm picking up everybody from that pile, right? And I'm arranging them in a certain order, right? Notice that the N minus N would just become 0, and so it ends with 1. It ends with 1. Okay, so that is P of N comma N is N times N minus 1 times N minus 2 times dot, 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 3 times 2 times 1, right? You count all the way down to the integer 1. Or you can think of this as the product of all integers from 1 up to n, some number, some positive integer that you care about. And we have that. Does anyone recognize this number, what it is? Does anyone know what that is or what it's called? Seen something like this before, heard of something like this before, know a name for it? No? Well, it's called N. Not N, like you actually write an exclamation point, but it's not read an exclamation point. It's read N factorial. It's called a factorial, okay? So when I write N exclamation point, what it means is I'm writing down the product of all integers from 1 up to N. So for example, P of 5, let's look at it from the perspective we want to look at it. P of 5 is 5 factorial. That is 5 times 4 times 3 times 2 times 1. And that is 120. And that would be, for example, the number of ways to line up 5 people in order. Okay. So in other words, your N factorial is the number of ways to arrange in some order n objects. Or maybe I should state that a little bit more concisely. Number of possible arrangements of n objects. Okay, so that is n factorial. And I do want you to appreciate now why combinatorics is going to be so useful, because you wouldn't want to have to actually list out all of these possibilities, right? So you have 5 people, you know, John, Mary, Tom, Dick, and Harry, and you want to arrange these people in a line. You don't want to have to say, okay, well, I could put John first, then Mary, then Dick, then Tom, then Harry, or I can put Mary first, then John. Like, you don't want to have to, you would be writing down 120 things. Ain't nobody got time for that, right? You should just know, like, how many ways I can put these 5 people in order. 120, right? We know that based on the fact that what I'm really doing is a permutation. I'm putting them in a certain order. So I'm thinking of them as tuples where I can put anyone in the first position, but I can only put 4 people in the second, 3 people in the third, 2 people in the, and so on, right? And so I can know that that's how many ways I could do it without specifically writing down all the ways. I wouldn't want to have to list 120 ways, right? And arranging 5 things, come on, that's nothing, right? We're going to want to arrange many, many more things, right? So when you want to arrange everything, you use a factorial. When you want to arrange a subgroup, then you can use the permutation. So to go back to another example, if I were to say, for example, there are 10 people standing over there, and you just want to choose 3 people at random to create some committee, right? You're going to choose someone to be the president and someone to be the vice president and someone to be the treasurer, right? There's an inherent order there. And of course, there are no repeats. You're not allowed to choose, once you choose one person and put over here, you can't choose them again. And so P of 10 comma 3 would be the number that you would choose, the number of ways you could do that if it was completely at random. So yeah. When it comes to counting things in order, permutations and factorials are very useful. There is a very special case, again, by convention. And this is for many reasons. We define the number 0 factorial, right, to be 1, right? So this is 0 factorial. This would be read as 5 factorial. Right? We define this to be 1. Now, there are a lot of mathematical reasons to do this, but there's also good conceptual reasons to do this. How many ways can I arrange 0 objects? There's one way to arrange 0 objects. No one can come to you and say, well, I found a different order to put these 0 objects in. Like, no, you didn't. Like, how did you rearrange the order of 0 things, right? So there is one way to arrange 0 objects, right? So conceptually, we want 0 factorial to be 1. Now, there are a lot of mathematical reasons for this as well, but for now, we can think of it that way. 0 factorial will be the number of ways to arrange 0 objects, which is 1. There's no other rearrangement. It's just whatever is not there at the moment. Now, we can write PNR in terms of factorials. So more concisely. Okay. So how would we do that? So let's say I have P of n r. This is n times n minus 1 times n minus 2 times n minus r plus 1. So we're going to do this thing that math people do sometimes to try to be sneaky and do get something in a nicer form, is to multiply and divide by the same number, which is what we're going to do here, but I don't like how I wrote that n. Is to just continue and go, well, the next would be n minus r, then n minus r minus 1, then n minus r minus 2, dot, dot, dot. Go all the way down and complete the arrangement. Similarly, we divide by that same number because I essentially want to multiply by 1, so I'm not changing the value of the number. So I multiply and divide by that expression. What you will notice is that the numerator is just going to be the product of all numbers from 1 up to n, right? It's 1 times 2 times 3 times going all the way up to n. So this is just n factorial, right? So that part here is n factorial divided by this part here is the product of all integers from 1 up to n minus r. By definition, this is n minus r factorial. So, i.e., p of nr can be thought of as n factorial divided by n minus r factorial. And if you're familiar with permutations and you've seen them in textbooks, chances are that is how they were presented to you as a formula. Now we know where that formula comes from, and we know why it can be written in the way that we wrote it. So it's probably cool. Let's keep going. Now we know how to count tuples in various scenarios. And this is useful when order and or repetition is useful when order matters. When order matters, repetition may or may not be allowed. Okay, so when there's no restriction, repetition is allowed. I want to create a tuple of size r from a set of size n. There is n to the r such ways, such tuples. If I wanted to restrict repetition, like I don't want repetition, then this is the number of ways, which I can write it as n factorial over n minus r factorial. If I want to take all the objects, arrange all n things in a certain order, this gives rise to what's called a factorial, n factorial, number of ways to arrange n objects. Okay. But what if we wanted a little less restrictions? So what if we wanted no such restrictions? Like order does not matter. repeats, not allowed. Then we need to count sets. Then we need to know how to count sets, right? Which is going to be the section we're going to end with. So suppose A is a set of n elements. And again, R is somewhere less than n. How many sets of size R can we create from the elements of A? Okay, this is going to be what we want to be able to count. I'm going to show you with a couple examples. Example, suppose your A is A, B, C, D. And I ask you, how many 2 sets can we create? Well, you can actually go through and you can number all of these. So enumerate them. So I can have A and B, I can have A and C, I can have A and D, I can have A, that's it. But I can also have, say, B and C. I could have B and D. I could have C and D. And I think that's it. So what I just did was enumerate. And here, there are 6 possible sets. Right? So I just arranged them in, just took 2 elements from the set of size 4 and created subsets of size 2. There are 6 ways that we can do that. But how can we come up with that number 6, especially in a more crazier scenario? So let's make this harder. Example, A is A, B, C, D, E, F, right? So the size of A is 6. If I were to ask you the question, how many 4 sets can be created? Right, so I'm asking, for example, I could create a set like A, B, C, D, or I could create a set like B, C, E, F, or I could create a set like C, D, E, F, etc. Right? I can create sets of size 4. How many of them would there be? Suddenly, this thing that I just did up here doesn't seem so fun anymore, because now I'm going to have to worry about all arrangements. And then you're going to realize that you have repetitions coming in. So for example, this set is the same as BACD, which is the same as CADD, right? And you're going to go through this exercise and you're going to figure out that you're going to realize that you created a set that you already created. And like, damn it, I already have that one. Because you have a different arrangement, it's not going to matter. This is harder to count. Let's be clever here. So take one such set. I'm going to figure out how, in terms of things that we've already done, what is a number I can associate with a set? Take one such set. Say A, B, C, D, right? If I were to ask you, how many set representations are there? Right. So this means you could have A, B, C, D, but that's the same as, say, B, A, C, D. That's the same as D, B, C, A. That's the same as, you can actually write down this set in many ways. And what I'm asking you is, how many ways are there? So let's see if you can, who's been paying attention, maybe you can quickly guess because we're already a couple minutes over. How many ways can you write that, do you think? $12. Thank you for the guess. That's not correct, though. So here's how you can think about it. What I'm actually doing to get a different representation is I'm rearranging the things in the set. So what I'm asking is, how many ways could I rearrange the A, B, C, and D? I give you 4 things, A, B, C, and D. How many different arrangements do I have? Well, 4 factorial, right? It's the number of ways I can arrange the 4 elements. So thank you for your guess, but that's not what it is. 4 factorial is what it is. We can arrange it in 4 factorial different ways. Right? To generalize, we can see that for every set of size 4, there are 4 factorial different set representations. In other words, if I look at my sets as tuples, as I'm doing here, just counting the different rearrangements as a different thing, what we can realize is that for every set of size 4, number of 4 sets, 4 factorial times whatever number that is going to give me the number of 4 tuples, right? Where the tuples care about the order, the rearrangement. For every 4 set, there are going to be 4 factorial different arrangements of the elements to be written down as a set, which I can think of as an ordered set, which I count differently, which is like a tuple, right? So in other words, this means that the number of 4 sets or sets of size 4 is going to be equal to the number of 4 tuples over 4 factorial. Now, what is the number of 4 tuples? Well, that's a permutation, isn't it? That's the number of ways that I could have chosen 4 objects from the 6 objects. So that's the number. In other words, this here is going to be 6 factorial over 4 over 2 factorial. Let me not write that down here. I'll rewrite that later. We can generalize this. the number of R sets that can be created from a set of n elements is, well, P of n choose R divided by R factorial. And this is an important number. We denote it C of nr and call it a combination. That's what the C is for. Combination because the order doesn't matter. It's not an arrangement. It's just me combining stuff from another set. It also has other notations, just like the PNR. So you have NCR, CNR, NCR, NCR, right? It's called a combination. I want you to also note that PNR over R factorial, by definition of PNR, this is n factorial over R factorial times n minus R factorial, n factorial over n minus R factorial, but then that's divided by R factorial. So that leads to n factorial over R factorial times n minus R factorial. And so we get CNR equals n factorial over R factorial times n minus R factorial. It's called a combination. It is read n choose R. And what that means is that CNR, this is the number of ways to choose R objects from n objects in no particular order. Order doesn't matter. So that's the combination. I don't think I want to give you anything else in the notes right now. I will say I do want you to know how to do these on your calculator. So I'll leave you with a couple examples. Try to find these in your calculator. Tell me tomorrow. So this is C of 25 to 7 and P of 34, 9. Try to do those in your calculator. Tell me what number you get tomorrow. We'll continue with some counting principles and counting examples, and we will put you guys in your groups and give you the group project, which is going to be due in about a month. But that is it for now. Thank you for your time and attention. Hopefully you have a good rest of your day. I'll see you guys tomorrow in the next one. Ciao.